I am Mariusz Dąbrowski, and I am the president of the Jerzy Stelmach Eureka Foundation, which deals with interactive education and popularization of frontal scientific research. The foundation gathers active scientists, and therefore, for a couple of days, we offer the lectures and debates under the project Science and Technology Progress Closer to the Society. This is a session which is technical session, T3, which is entitled Modular and Advanced Reactors, SMR and AMR, for Sustainable Development. The project is co-financed by the Polish Ministry of Science and Higher Education under the Social Responsibility for Science II program, and its aim is to bring the achievements of science and technology to the general public. I am pleased to announce the next in the series of lectures about SMR and AMR technology today. We have heard a general lecture about this, and also some specific lectures yesterday about BWX technology, and today about HTGR technology. Now, today, we have a guest, Mr. Andrea Barbarino. Hello, Mr. Barbarino.
Hello, Professor Dąbrowski. Thank you for the invitation.
Thank you very much for agreeing to actually say something about your technology in front of our Polish audience. So, Mr. Andrea Barbarino is working in LFR engineering department, safety and plant analysis division, and he is the manager of this division. So today the title is Molten-metal-cooled reactor LFR. How does it work, and what is the perspective of its implementation? You will learn, but this is the company, Newcleo company, who is actually running this project. Mr. Andrea, please start your presentation then about the technology you are working on.
Yes. Thank you very, very much. I'll give this speech about the technology we are trying to develop in Europe and elsewhere, which is one of the liquid metal reactors technologies that exist on the world. It is the lead fast reactor. I have a few slides. I share my screen.
Yes,
in a moment, so that you can, so that I can use some pictures to show you how it works. So yes, I work in the engineering department of Newcleo. I'm based in Italy, but we have offices also in France with the engineering staff. And I joined Newcleo in 2022, the beginning of the story of Newcleo. Basically, Newcleo was born in 2021. When I joined Newcleo, I had worked 10 years for the nuclear power plants in France, and then I left France and I joined a startup. At the time, we were 30. Now we are more or less 1,000 all over Europe. So it's a very, very, very exciting company that grows very, very fast. I tried to make an introduction because it's a little bit hard to talk about the lead fast reactor without knowing a little bit which kind of nuclear reactors are used today, which kind of nuclear reactors have been imagined in the past, and how we came to this concept, this innovative concept, and why. So please be patient. A few minutes, I will tell a little bit the story of the development of nuclear in Europe and in the world. So today, when we think to a nuclear power plant for power production, for electricity production, we think to a certain paradigm. We think to the light water reactors that use fission with thermal neutrons as the physical mean to produce this power, and basically that are very, very large. This is a real plant located in France, but anyway, a little bit all over the world. When you see a nuclear power plant, well, you recognize it from very, very far. This is just one way to build nuclear reactors. Okay, it's a paradigm. It's what I call a paradigm, a generation 3 paradigm. It's a certain technology that uses water. Is a technology that uses a certain physical phenomenon, the fission with thermal neutrons, to produce power, and that has chosen to be large in size to profit of scale economy. It's like this basically from the beginning of the nuclear era, from the 50s, more or less. Yes, this was the kind of power production that was identified as the easiest to build, the more economical, the more scalable, etc. And so industry has invested a lot in this paradigm. I like to make a parallel with cars, where we all have known the classical cars that work with thermal motors, that work with petrol or diesel. And basically, this is the winning technology that has been developed from the beginning. If you look back to the Ford Model T, well, okay, you cannot compare it directly to a modern Ferrari, but in any case, you see the same components. They have dramatically improved, but the basic concept is the same as being developed, and the performances in terms of speed, in terms of consumption, safety, have been ameliorated. Well, for the nuclear power plants that we know today, it was the same. The power plants imagined in the 50s have evolved and have become this kind of installations. It's not the only way, and since the 50s, since the very beginning, people have started to question if these three hypotheses were the best one. So, is it possible to have a nuclear power plant that uses a coolant which is different from water, but that has some drawbacks? It's easy to have, but have some drawbacks. Is it possible to profit of nuclear reactions which are not fissions with thermal neutrons, but something else? Can we use fast neutrons, which are more powerful? And is it the large size, the best one, economically the most viable one? Do we have some interest in building small size plants? These questions were cultivated essentially by research and development, and there was an acceleration of the interest in these questions at the beginning of this century, where the generation 4 activities were launched. So there were many ideas and 6 kind of innovative reactors, advanced reactors, eventually modular reactors, were selected to be sufficiently founded, to be covered by more studies, etc. They are very different in kind. You see that they destroy the original paradigm in different ways. So there are some reactors that are fast, so profit of this different way to use nuclear fission. Some are still thermal, of course. Many use different coolants. So some are still using water, but we introduce molten salt, gas, lead, or sodium. so molten metals. And it's not evident here, but most of them are made to be interesting already with small size, with small power. A little note about this difference between fast and thermal neutrons. Enrico Fermi, the person, the Italian scientist that during the Second World War created the first nuclear reactor, already said one thing in 1945 that it's illuminating. He said, okay, we will develop thermal reactors because they are easier to build. But the breeder reactors, which is another name, I simplify a bit, for a fast reactor, is more interesting. And the first that will be able to have a fast reactor technology, which is commercially viable, which is industrial, we have a great competitive advantage in atomic energy. And basically, we, together with all the stakeholders of the Generation 4 forum, we are a little bit following this intuition because we really believe that he is right. Which are the advantages, the competitive advantages of fast reactor? So just to come back of this section of the Generation 4 proposals. Well, there are many advantages. I'll try to go straight to the most interesting ones. All nuclear reactors rely on this material as a fuel. Okay, as cars rely on oil, we rely on a mineral which is uranium. In, say, thermal classical reactors, this uranium cannot be used as such. You cannot insert directly uranium into a light water reactor because inside this material there are two isotopes. There is the uranium-235 and uranium-238. The vast majority is 238, and really a few percentage are 235. Classical reactors can only use the 235, the few orange dots that I have put in this picture. So to be used, it has to be enriched, it has to be filtered, let's say, and then this can be used to produce electric energy. So from this process of enrichment, you get a lot of useless uranium-238, which contains a little bit of 235, but it cannot be used in nuclear reactors. It is not dangerous, but in any case, it has to be stored. It's a waste. And then, as you know, once you use this enriched uranium into the reactor, well, you get some very dangerous waste. Waste is made basically of remaining 238 and 235 because these reactors are not very efficient in using this fuel. And then fission fragments and plutonium minor actinides. The very long-lived, dangerous, and nasty waste components are these two, the red ones, the fission fragments and the minor actinides. But the volumes are quite important. Okay, so all of this is the nuclear waste that has to be treated, and it is a problem. We don't know how to store this properly. We don't know how to say to the future generations, hey, pay attention, we have stored here this kind of waste. The life of all these summed together is very long. It will remain dangerous for tens of thousands or hundreds of thousands of years. So this is also an acceptance problem for nuclear. Well, fast reactors don't care too much of this difference. Indeed, they don't look to the 235, but are able to use the 238. They transmute the 238 using these fast neutrons to something else, to plutonium, and then they fission plutonium. So there's no need to separate all these 238 because this is fuel. This can be used. And also, some of the waste, the plutonium minor actinides produced by light water reactors can be fissioned again, because fast neutron can fission these elements that thermal neutrons simply not, they ignore. So also the waste of light water reactors, also the waste, the activated waste of the light water reactors can be used to fuel a fast reactor and to produce electricity. So I guess you imagine this is a great advantage. We use much better the uranium resource, and we also remove some of the dangerous components that are produced by light water reactors. So it's a complementary technology to light water reactors. We use their waste, but we use it much better than they can. So we finish using the fuel that we have started using in light water reactors. Concerning lifetime of this waste, water reactors, as I told you, have produce waste which are very long living. So after 250,000 years, we still see their dangerosity. It is reduced, but in any case, you cannot manipulate them as you would manipulate a non-activated material. With fast reactors, indeed, and with some treatments, you can achieve a great reduction in the volumes and a great reduction in the life of this waste. So you can hope that after 250 years, you can again manipulate this material safely with no protections. This does not mean, of course, that you solve the problem of nuclear waste at all. 250 years are a lot. You still need to have special places to store them. You still need to say to the future generations, pay attention. I have put in this special place some very dangerous material. Don't touch it. But we do this already for some other chemicals, for some other materials that we have to produce for industry. Is complicated, it's not evident, but this is not let's say, it's not a specific problem of nuclear. Managing waste for 250,000 years is extremely complicated. Basically, we don't know how to do. We don't know how to write to a future generation to pay attention to this material. We don't know which language will be used in the next 250,000 years. So it's a big unsolved problem that fast reactors can solve. And then the third part of the paradigm is large necessary with this kind of reactors. Is the profiting of the economies of scale necessary to have a production of electricity that can be sold on the market? Well, for several reasons, this kind of reactors can be made also small, and there are studies that show that they are economically viable also for smaller sizes. The fact of having an electricity generator which is smaller have also other advantages. Not only it costs less, but it allows also the modularization. When we talk about advanced modular reactor, we say often that we want modularization. This means two things: the possibility to have a plant in which we add more reactors to have a wide spectrum of power sizes to adapt to different environments, to different countries, to different customers. But also that we can build modules away in a gigafactory, for instance, and then transport these modules and assemble these modules on site, or eventually transport the entire reactor directly to the power plant. This is impossible with large size reactors that must be assembled on the site, on the plant, and these phases are very long, very costly, etc. We can really start to think of a serious production of this kind of reactors and profit of the advantages of serious production. This was really a brief introduction to the to the concept. I hope I have suscitated in you some interest in the fact that we can think differently from the present paradigm. Nuclear is not necessarily big, it's not necessarily made of a certain technology. There are other possibilities that can be explored. In the past, some possibilities have been explored already. They were not successful. They have always found some technical issues that have a little bit stopped the development. But in any case, there are some nice installations from which we can start copying something. In the field of the liquid metal reactors, probably one of the first realizations were made by the Russian scientists that have built some nuclear submarines using lead reactors, not lead fast reactors. They were hybrid reactors. They basically replaced water with lead, but the rest of the reactor look similar to a water reactor, let's say, more similar than an LFR. And they built a few examples of this. They built 7 submarines powered with these liquid metal reactors. They dismissed them in 1996, quite early. There were a lot of technical problems, but in any case, they started exploring these strange coolant, lead, and they started to accumulate data on its behavior. I think that nobody before them was ever interested in things like the viscosity of molten lead or the heat exchange characteristics with water in tube heat exchangers. Okay, it was really a first test rig to explore this field. The champions of the liquid metal reactors, and this time liquid metal fast reactors, my opinion, were absolutely the French. They were able to build three liquid metal fast reactors in their history. The biggest one is Superphénix. Superphénix is not far from here. I'm in Turin. Superphénix is close to Lyon in France. It was built in 1986 and produced electricity for about 10 years, let's say. It was really big size. It was a big producer of electricity. I have a scheme in this page. In French, they say un vue d'artiste. So the picture made by an artist. Unfortunately, we don't have these kind of pictures for LFR yet, but you can see, I hope, the size of a person there, just to imagine how big was this machine. How this machine was made? Well, the most important part is this one, this container, this tank, which is the primary system, and inside there is the core. The uranium and the plutonium is contained in this red area. The rest of the tank is filled with sodium. Sodium is a metal that melts at low temperature, about 100 degrees, that is used to receive the power produced by the core, receive the power produced by the nuclear fissions, and then transfer it elsewhere. What we don't see here is that outside there was a steam turbine that used steam produced in the steam generators here to generate electricity. This concept is really the inspiring concept for lead fast reactors. Many of the people that have created Newcleo have worked in this project, have seen this reactor work, because this worked very well, have seen the drawbacks of this technology, and have started to think, maybe using sodium is very good, but there's something better. let's think of replacing sodium with lead. And let's adapt this concept in order to take into account the specificities of this new coolant. This is really the origin of lead fast reactor. Is a modification of sodium fast reactors to counter some problems that this kind of plants have. I have another picture always of Superphenix. This is a zoom of the reactor part. You see the tank. You see in yellow the sodium. You see the core. The core is made of sticks of fuel assemblies in vertical position, and then you see big components coming down from the roof that are needed to move the sodium. This is the pump, or to extract power from the sodium. This is the intermediate exchanger. And then you see a lot of structures to sustain the core, a lot of instrumentation and structures, concrete structures around. Keep in mind just this picture because I will use it to explain what a lead fast reactor is. So let's come to the concept. Let's come to the Newcleo concept. Our reactor looks like this. You see, we still have a tank. We still have the vessel, okay, in U shape that you see here as Superphenix. We still have a core, which is made of fuel assemblies. This sticks. The nuclear fuel is contained into this region. We still have a lot of things that come from the roof, that hang from the roof. But we have some notable differences. In Superphenix, you have seen that there were two big components, one pumping sodium into the core and the other one extracting the heat. Well, we have condensed everything in a single component, which is the steam generator and primary pump block, which is here, which is very compact and which can also be inserted and extracted as a single component. So also from the handling point of view, it is much easier to be treated than the Superphenix components. We still hang everything from above, but please check, we don't have heavy structures at the bottom of the vessel, while in Superphenix there were a bunch of structures there. We just have some features to direct lead and to avoid that the core oscillates, but no heavy structures there. And another specificity is that this is not an intermediate exchanger. This is a steam generator. So from this block, we directly output steam. There are other very interesting components, innovative components. Basically, every component here has an innovative design. It resembles to the one of Superphenix, that we are designing really every cubic centimeter of this stuff, because since it is immersed in lead, it's we cannot copy Superphenix technology. We just take an inspiration that we are compelled to modify basically everything. Another component is the decay heat removal. So for startup and shutdown, we don't use the steam generators to remove power, but we use an alternative mean, which is more flexible and also more reliable in case of emergency situations. And we have another strange component that you can't find in Superphenix, which is this inner vessel that is used to separate the hot part and the cold part. It has the shape of an amphora, and so we called it the amphora inner vessel. And design, the design takes the name of this very peculiar component, is the lead fast reactor amphora-shaped design. To go a little bit more into the details, I have to compare with Superphenix. It's easier for me to explain the gain of this design if I keep the picture of Superphenix in the background. First, the size. We are much smaller, as I told you, 6 meters against about 20. Of course, we are smaller. We produce much less electricity. But as I told you, this is a modular concept. So to make a power plant, we can put many of these reactors in the same place, and so easily with 6 units come up exactly to the same energy output. So say size is not a problem. But we can manufacture remotely, we can transport a lot of these components very easily on road, while on Superphenix, well, transporting these kind of things was really, really complicated. Again, check here in Superphenix. Here you have the core, and here you have the steam generator. Okay, so here is where you produce your power. Here is where you get the steam, that is the thing you use to produce electricity. A lot of space in between, and a lot of things. There is an intermediate circuit, starting from the intermediate exchanger, that has to transport sodium up to this place, basically outside the reactor hall. Why? Because sodium has a big drawback. It is extremely reactive. If you look on YouTube, sodium experiment, explosion, etc., you will see that if it comes in contact with water, it has a very energetic reaction. So the designers of Superphenix thought, and they were right, that it was too dangerous to have an heat exchanger with water here. In case of problem, in case of failure, in case of a passage of water into the sodium, basically all these reactors have taken fire or exploded, and of course the core would have released a lot of radioactive material with serious impacts to the population around. So they have decided to take this sodium and make this dangerous component, this contact, almost contact between sodium and water, very far from the core. But they had to add all these pipes. This is a pump, a circulating pump, a lot of instrumentation, of course, a lot of concrete to be able to sustain this intermediate loop. Well, we don't have it. We don't have it at all because we can afford to have water inside the lead pool. Lead and water do not react energetically one each other. So in case of failure, yes, we have a production of steam. We can manage it, but we don't have an explosion. We don't have flames. We don't have generation of heat. Just a steam that has to be evacuated outside, but nothing else. So we can remove completely all the complexity of the intermediate loop of Superphenix and have something which is more compact. We can have here directly the steam turbine connected. Another advantage is that we have displays and we can use the pumps. Another drawback of sodium fast reactors is that you can't put the pumps in the top part of the reactor. You have to push sodium towards the core, and to push the sodium towards the core, you typically have to put some pipes well under sodium. These pipes are then very delicate, very difficult to inspect. Once you cover with sodium, you cannot remove sodium just to go there and have a look. The French have developed several technologies to see to make inspections under sodium. Very brilliant, but it remains complicated. We totally eliminate this kind of ducts, and we have, as I told you, something which has no pipes, and then that can be removed if we want to check it. Can remove, put in a hot workshop, and then put back quite easily. This, once installed, it remains there until the commissioning. Second interesting advantage Well, I told you that the core is there, is made of assemblies there. The core slowly bursts the nuclear fuel. So these sticks, these assemblies must be regularly changed. How the French did this into their sodium reactor? Well, again on the picture, this is the core. They took the assemblies one after the other with this machine, with this in-core refueling machine. They raised them. They moved them to a lateral position here, and then there was this another very big X-vessel machine, this sort of compass, this inverted Y pipe that took the assembly, made it change direction, and then stored in another pool of sodium. So the problem is that you have a dangerous pool of sodium here. Well, in this kind of reactors, you have two pools of sodium, also molten sodium, also reactive. It reacts with air, reacts with damaged assemblies because it reacts with fuel, etc. You have a second one, okay? You use the second one to wait a bit that the assembly has cooled down, and then you can evacuate it to outside to a classical water pool. Again, this is very complex. Two machines and another intermediate storage full of sodium. The lead fast reactor, the Newcleo concept or lead fast reactor allowed to have a single fuel handling machine, which is not here, but can imagine it's outside of the reactor, that extracts the assemblies. The assemblies are very long and go up to the surface of lead, which is more or less here, and are received by this machine and put directly into a spent fuel pool. So only one machine that extracts completely the assembly. She hasn't got to go down to look them because the head of the assemblies is already there. It's outside. It's above lead. So you just need a camera to select the right one, and then there is a gripper that takes it and extracts. It's from the technological point of view, I cannot enter into the details, but it's really much more practical, much more fail-safe. It's also very practical to check if all these assemblies are healthy. In Superphénix, the core, well, was heavier than sodium. So it needed all these structures, these white structures below it to be sustained, to remain in position. It's very important in a fast reaction, in the fast reactor, that the core doesn't move. But again, the structures were under sodium, so it was basically impossible to go and check if there were still earthy, there were no corrosion, no cracks. We don't have these kind of structures. All our assemblies hang from above, and so we can, just with cameras or with robots, check if these structures are in good shape, and so if the core below has maintained its original geometry. And in case of problems, we just retire. We can replace everything in this area from the first to the last assembly, no problem at all, throughout the life of the plant. So lead fast reactors, it's a different technology, comes from sodium, but have solved many of the issues that prevented the commercial success of this kind of reactors. Just a picture. This is our artistic view of how a Newcleo power plant will look like. It's much smaller than the Superphénix one. The footprint is notable, but we also include all the classical buildings that we need to produce electricity. So this is the conventional island. These are the aerogenerators to avoid using rivers to cool down the turbine. A lot of offices, warehouse. The nuclear part is just this rectangle here, and we plan to put not one, but many reactors in a single nuclear island to scale the power and the needs of the customers. The fact that our reactor is small enables also us to think to very innovative, very breakthrough ideas, like putting this kind of reactor on a floater. This is a concept that we are developing with one of our partners, Saipem, and one of its subsidiaries, Moss Maritime. We are thinking if we can use a sort of oil rig that is already available for oil and gas applications with a very important payload, to put one or more reactors and to have a floating power plant that can be moved where there is a need, or in any case that can feed some specific customers like oil and gas sea fields. It's a very interesting application, very challenging. From the technological point of view, we think that there are no showstoppers. We can adapt our concept of reactor to this very strange environment. We have to analyze what does it mean to license, to authorize this kind of applications in the countries that want to do that, because for the time being, countries are not ready to license these kind of applications already. Not all of them are ready to license a nuclear reactor. You can imagine a floating nuclear reactor. There are no rules, no laws, etc. So we are also exploring what the state should do to profit of this technology and to license in a reasonable time these kind of reactors. Since we are getting long, well, Newcleo has also a program, very interesting, I have no time to enter into the details, to manufacture its own fuel. So to manufacture the core, the fuel elements. These require specific technologies. Just a few countries know how to build MOX fuel assemblies. Well, we want to develop our fuel factory in order to be autonomous once someone gives us the plutonium from reprocessing. Just to conclude, I go to the most, in my opinion, the most exciting aspect of the activities of Newcleo nowadays, because, well, for the time being, I've shown you nice pictures of the reactor, okay, but we haven't built it yet, and we still need some time to build it. And this happens often in the nuclear field, especially when you think about generation 4 reactors. They are paper reactors, so as a scientist, you study all the aspects of these reactors, you simulate it at a very fine level, but you don't see them built, you don't see lead or sodium or molten salts flowing into something. And we are basically engineers, we want to see this thing built, and we want to see our ideas that take life and that work. We have a lot of R&D to do on these reactors. They are almost ready, but as we say in Italian and in French, the devil is in the details. There are many aspects that must be studied yet. Lead is a wonderful coolant, but it is corrosive, and if it goes too fast, it's erosive. So we need to optimize the materials we use for basically everything to resist to this combined effect of corrosion, erosion, and also the effect of irradiation, because this is a generator of fast neutrons that damage the structures slowly but inevitably. We have to demonstrate that all the features that we put in this reactor are very reliable, otherwise no one will ever license this reactor. And since we built this feature for the first time, well, we have to test them in advance very, very well. we have to demonstrate that some phenomena that work very well on paper and work very well on the codes work very well also in reality, that there is not something that we are missing that, for instance, counters the natural circulation we want to use in the case of emergency and other aspects. To do this, to do all this research, well, Newcleo has really a competitive advantage against basically all the other startups because we have found a lot of investors, we have found strong partners, and we are building a gigantic research center where we are putting a lot of test rigs to test all these effects, to test several phenomena, to test several technologies related to our LFR reactors. This list is not complete of the facilities that we have built, we are completing, or we will build in the next few years in our main private research center, let's say, which is the Brasimone site. The Brasimone site was one of the sites of the ENEA, the Italian research center for nuclear applications, that was dismissed. A nuclear power plant was planned to be built there. The construction was stopped in 1987 when Italy decided to stop all the development of nuclear power plants in the state, and so well, it seems like a nuclear power plant, but indeed was just a bunch of old structures starting to ruin inevitably. At the very beginning of the Newcleo history, we signed an agreement with ENEA, basically to rent this enormous site. ENEA had some facilities in the former reactor hall, but for the rest, there was absolutely nothing. I visited this site in July 2022. I told myself, okay, it's just concrete, nothing else. What we want to do here? Well, in a few years, we are completely changing this site, and we are installing very massive installations there, which are really exciting to see and, of course, to design. First, there was a campaign of refurbishment. We had really to make some hard works. One maybe of the most complicated and surprising was to change the electrical installation because, well, we need a lot of power, electrical power, to be delivered on site, and the transformers was not ready to get it. So we had to remake basically all the electrical distribution system of this place, and then we started to design all the facilities. Well, taking a lot of space to the ENEA colleagues that are now compelled to remain in a corner of this site because all the rest has been absorbed by our activities, by Newcleo itself. The list is very long. I just want to introduce you the biggest facilities that we have. One is Othello, is basically completed. We completed at the beginning of next year. Othello is a loop, so it's a pipe containing molten lead and some components that mimic the components that we will have on the reactor. This is a short, flat version of the steam generator. There is here a pump. There is here a mock-up of the fuel assembly, the hexagonal fuel assembly with all the elements, all the sticks of uranium and plutonium. In our case, are electrical heaters. It's not nuclear fuel. And we will test here several components. We will partially qualify some components. We'll extract a lot of data that we need to finalize our design. This loop, if seen like this, seems very simple. If seen in the rendering and in reality, it's enormous. It's 6 or 7 stories high, a lot of structures because lead is very heavy, so it has to be kept in place. A lot of electrical cabinets, because in any case it will be heated and will use 2 megawatts of electrical power. So also these kind of features take a lot of place, and it's growing. This was a picture taken this summer. You see only this part, but the rest of the circuit is almost complete, and when you see it, really is astonishing. But Othello is the let's say the smaller brother of the Precursor. The Precursor will be the biggest facility we will ever build before building, of course, the reactor. Still, it will be electrically heated, but will resemble a lot to our reactor. It will just be slimmer, but for instance, the height will be the same, because we really want to test the concept of the LFR without the nuclear fuel, but in a much more complete way. We want to see all the interactions between lead and the different components. We will have steam generated by the steam generator, while on Othello, no. And we will put this steam on a small secondary circuit with a small turbine, a small condenser, in order also to see if this machine can be easily operated by the operators, because in the end, a nuclear reactor is quite automatic, but there are humans that have to understand, have to anticipate the behavior of the system. So they have they must learn how to use this reactor before we build it. And so the Precursor will be our final test rig for them. If Othello was big, this is even bigger. This is 10 megawatts of electric power. 10 megawatt is a high-speed train at full power, for instance, and full load, of course. But here, all this 10 megawatt will be expressed in a small volume and via electric heaters. So it's a powerful machine. And if you look the picture of the Brasimone site, you can easily see that this installation will be gigantic. It will almost be an entire power plant with all its auxiliaries in place to serve as a test. This is going to be installed very soon. The planning says more or less in 2027, but we are starting to see the preparation works and some parts of this circuit at the Brasimone. So thank you very much. Sorry for having said many things in a short time, but the development of LFR and all the things we do in Newcleo is a very long story and very exciting. It would deserve years to be told. In any case, if you have some questions on specific aspects, I'm here.
Thank you very much, Andrea, for this excellent talk. Your excitement, and I can see this number of people who are surrounding you and your managers is wonderful. So this vivid work will surely end up in constructing this reactor, I am sure. So this is a transmission to the Polish audience. Yes, please trust us that nuclear technology nowadays is developing very very quickly and widely in many aspects, exactly in terms of both SMRs, light water, small reactors, and AMRs, which are advanced and have lots of advantages, which actually was presented during this talk. So let me check if there are questions. I don't see questions on YouTube and also on Zoom. Anyway, thank you very much, Andrea, for presenting this talk. Thank you very much, our audience, for watching us both on Zoom and YouTube. And I would like to invite you for the next lecture, which will be in 2 hours, and it will be devoted to molten salt reactor technology, given by Professor Tomasz Kozłowski, and then a final discussion which will take place in 3.5 hours on our YouTube channel. So let me remind you that you have been watching the lecture about SMR technologies, nuclear technologies, on our channel. Watch us on the YouTube channel Fundacja Eureka, www.youtube.com, then Fundacja Eureka. Thank you very much again, Andrea. Thank you very much, everybody. Have a nice afternoon. Goodbye.